All right, here we are with 4.1. We're in chapter 4. Awesomeness. All right, so we're looking at exponential functions. All right, so we've probably seen exponential functions before. We're just going to take a closer look at them along with some transformations. All right, so an exponential function with the base a is defined for all real numbers of x by the function f of x equals a to the x power or y equals a to the x, where so the base needs to be greater than 0 and it can't equal 1. So it can be any number from 0 to 1 and then from 1 to infinity. Can't be negative and it cannot be 1. So here's the question. Why the special conditions on the base? Well, let's take a look. If a were equal to 1, let's take a look at a table of values. So we have x and y, and let's just pick some random values. This is for y equals a to the x. Or sorry, 1 to the x. Because we're talking about when a is 1. Well, plugging in, let's say a negative value, negative 1, that's going to be 1 to the negative 1, which is still 1. How about 0? That's going to be 1 to the 0, which is 1. How about 2? That'll be 1 to the second power, which is also still 1. So if I graphed this, that would be negative 1, 1, 0, 1, 2, 1. In fact, anything I inputted for x, my y value would come out to being 1. So we'd actually just end up with the straight line y equals 1. Now that's a line. We don't want to look at lines. We're looking at exponential functions, okay? So because of that, because of how it ends up when we plug in values for 1, because of what it ends up looking like, we're like, nah, we don't want to include these in exponential functions. So we made a restriction. We being mathematician people-y, smart mathematician people-y, they said, we don't want a values of 1 to be included in exponential functions, so we're not going to allow them to be a part of this club. Sorry. All right, so let's look at who else they decided could not be a part of the club. A equals 0. Sorry, if a is less than 0. So we know a has to be greater than 0. What's wrong with a being smaller than 0? Let's pick a 0 value. How's about negative 1? So let's take a look at y equals negative 1 to the x power. Let's go ahead and do a few graphs on those. So if we picked x equal to 0, y would be 1. If we picked x equal to negative 1, y would be negative 1. Oh, wait, sorry, let me pick y equal to 1. If x was 1, y would be negative 1. If x was 2, y would be, well, it's negative 1 squared, which would be positive 1. And if x was 3, y would be negative 1. So if I was to graph this, we have 0, 1, 1, negative 1, 2, 1, and 3, negative 1. Okay, this ends up creating something that'll look sort of like that, which is also not what we're talking about when we're looking at exponential functions, okay? So because of the alternating between positive and negative signs when we use a negative base, we're like, we don't want these to be included in exponential functions. We're not going to include those. So the restriction for being less than 0 was put in. Because if we have a negative, the sign, it'll alternate and we'll end up with this weird zigzag. Okay, so those are for the two special conditions and why we don't allow them. All right, let's graph these babies. Okay, so 2x and g. All right, f of x. I'm just going to go ahead with the values of some positives and negatives. So negative 2, negative 1, 0, 1, and 2. Go ahead, pause the video, see if you can plug in those values. And then I'll go with the g values. Same idea. All right, so this is going to be 2 to the negative 2, which would be a fourth. 2 to the negative 1, which is a half. 2 to the 0, which is 1. 2 to the 1, which is 2. 2 to the 2, which is 4. Okay, plotting those. Negative 2, positive fourth. Negative 1, half, 0, 1, 1, 2, 2, 4. Alrighty, so here we go. Next one, xg of x. So that's going to be half to the negative 2, which is going to be 4. Half to the negative 1, which will be 2. Half to the 0, which will be 1. Half to the 1, which will be a half. And half to the 2, which will be a fourth. Alright, let's plot these. Negative 2, 4. Negative 1, 2. 1, 0. 1 half and 2. Oh, interesting. Look at that. They're kind of like reversing on each other in a way. All right. So, interestingly, here's a question. Could you ever raise 2 to a power and end up with 0? Is there any power you can raise 2 to get 0? Well, if you said 0, well, we can't do that. We get 1. If you pick a negative number, we'll end up with a fraction. If you pick a positive number, we'll end up with a number bigger than 2. So there is no possible way for y to ever equal 0. Okay, so we're actually ending up with a horizontal asymptote along here for both of these, because there's no way to make our y values equal 0. There's no exponential value, no number I can plug in here that when I raise 2 to that number, I'll get 0. It doesn't happen. Okay, so we do have that horizontal asymptote for this function. So let's look at the properties with this special form of just a to the x power. Okay, well the domain, if we look at this, positive infinity and negative infinity. So negative infinity to positive infinity. The range, well for these types, where it's just a to the x, we start from 0, we don't include it, and we go all the way up to positive infinity. Vertical asymptotes, we don't have any, none. Horizontal asymptotes, well, for this one, it's going to be y equals 0. Do we have any cross or touch points in the horizontal asymptote? No. Because that would be trying to figure out what value of x we can raise 2 to get 0. And that would never happen. So we don't have any cross touch points for our horizontal asymptotes. Y-intercepts, do we have any? Well, right here. 0, 1. Because for the y-intercept, whatever your base is, remember, you're raising that base to 0. So regardless of what the base is, any number you raise to the 0 power is always going to be 1. So in the form of a to the x power, our y-intercept will always be 0, 1. And any x-intercepts, well, for x-intercepts, remember, that's when we're checking. Make y equals 0. Can we raise a to some power to get 0? No, it doesn't happen. So none. All right, so that was the basic form of a to the x power. So now we're going to look at some transformations on our exponential function. So this is spicing things up a little. All right, so we're going to be filling in the table and sketching the graph of the parent function, f of x equals 2x, along with the given transformations. And then we'll be finding the domain, range, horizontal asymptote, and intercepts, if any. So for the parent function, y equals 2x. I'll be graphing this one in blue. So I'm just going to go ahead and pick a few values to work with, and then just use those for the transformations. So the x value of, let's go with negative 2. My y value is going to be 4. Yeah, that should go with positive 2, actually. Actually, no. I'll stick with negative 2. That's going to be a fourth. And then we'll go with 0. So this is going to be 2 to the 0, which is 1. And then we'll do positive 2. So it'll be a 4. Okay, so those are the points I'm going to be sticking with. actually, you know what? I don't like the fourth. I'm going to go with -1. So that would be a half. All right, let's stick that. I'm going to stick with -1. All right, so here we go. Parent graph, horizontal asymptote at y equals 0. Et voila. So my domain, go ahead and see if you can fill these out and check in with me in a second. Okay, domain, -infinity to +infinity. Range, 0 to infinity. Horizontal asymptote, yes, y equals 0. Y-intercept, 0, 1. Any x-intercepts? Nope, none. All right, now things are going to get fun. Let's take a look at this one. So, this next one, y equals 2x minus 2. What happens? Well, we are going to be shifting down 2 units. We have that subtract 2 on our function. Okay, so I'm going to take all of my values and shift down on the y's. So, a half minus 2 is going to be -1.5. So it'll be -1. Ooh, I just realized I didn't regraph that well. -1, 1.5. And then shifting down 2 units for that, that's going to be -2, so -1, 1. Oh, I did that wrong again. Shifting down on the y value, that should be 0, -1. And then shifting down here on the y value is going to be 2, 2. Because we're subtracting from the y's. And then, okay, this is the very interesting part. Our horizontal asymptote shifts as well. So our horizontal asymptote is going to shift down 2 units, which brings it to y equals -2. All right, that changes things up a little bit. Okay, so what's our domain? Well, it's still -infinity to +infinity, but this time our range has changed. It goes from -2 to infinity because we shifted down 2 units. Our horizontal asymptote got shifted. It's y equals -2. And our y-intercept is actually going to be 0, -1. And our x-intercept is going to be 0, 2. Sorry, 1, 0, excuse me, 1, 0. Right there. Okay, in a way, if you wanted to try find your x-intercept, let me do that up here. For our x-intercept, we set y to 0 and solve for x. Well, that would end up, well, let me do it on a sticky note. I'm going to run out of room here. So if you're trying to find your x-intercept for this graph, set y to 0. Solving for x, 2 to both sides. So the question is, what do you raise 2 to get 2? Well, the answer is 1. All right, so 1, 0. All right, so here we go. Let's plug in that new point, 1, 0. And the next one, y equals 2x to the 1 power. Let's do this one in green. So this one is we're going to shift. Okay, so the x, now that's with our x values. Okay, so these are x movements. So that's going to be shifting left 1 unit. Okay, so shifting left 1 unit from this parent graph. Let's see, so that's going to be negative 2 half. One, that's going to be negative 1, 1. And then that over 1 is going to be 1, 4. Okay, and then our horizontal asymptote has not changed. So there it is. All right, so the domain for this one is still going to be negative infinity to positive infinity. Our range is still 0 to infinity. Horizontal asymptote stays the same, hasn't changed. How about our y-intercept? Okay, our y-intercept, let's go ahead and find that. That's when we set x to 0. So y-intercept is going to be 2 to the 1 power, so that's 2. So my y-intercept is 0, 2. Let's see if we have any x-intercepts. So, using our function, we're going to set y to 0. Same problem here. There is no value I can raise 2 to end up with 0. So, none. All right, next one, got 2 more to go. Let's do this one in red. So we're looking at the function y equals negative 2x. Okay, so the negative is on the outside, which means we're going to be reflecting about the y-axis. Oh, sorry, the x-axis. Okay, so that means all of our y values get multiplied by a negative 1. So our horizontal asymptote is going to stay the same. That does not get affected. But these values, the y's get multiplied by negative 1. So that's going to be negative 1, negative half, 0, negative 1, and 2, negative 4. All right, graphing that in. All right, so when we're filling out, let me pull back on my paper here. Filling out this box here, my domain hasn't changed, still negative infinity to positive infinity. My range, however, has changed. What's my lowest value for my range? It's negative infinity until 0. I have a new range. It's the flip. Okay, my horizontal asymptote hasn't changed. It's y equals 0. My y-intercept has changed. It's 0, negative 1. And our horizontal asymptote is still on the x-axis, so we don't have an x-intercept. Woo, all right, one more to go for this. Let's see, what other color have I yet to use? I don't know if I have any other colors to use. Did I already use purple? I did. Looks like I'm going to have to reuse a color here. All right, let's go with... Actually, I haven't used black. Let's go with black. All right, last one. Y equals 2 minus x. Okay, so this time the negative is up with the x, which means we're going to be reflecting about the y-axis. Which means we multiply the x values by negative 1. Okay, so let's see, multiplying the x values by negative 1, that'll be 1 half. That'll be still 0, 1. Multiplying the x value by negative 1, that'll be negative 2, 4. And nothing happens to our horizontal asymptote. It stays the same. All right, let's see. Domain, still negative infinity to positive infinity. Range, same thing, 0 to infinity. Horizontal asymptote, well, that didn't move, so y equals 0. Y-intercept, didn't move, 0, 1. And x-intercept, well, my horizontal asymptote still didn't move, so still no x-intercept. Okay, so that's it. Just have an extra graph here. But those are some of the main transformations for my exponential function. Very interesting. Okay, so the only time we actually ended up with an x-intercept was when we had vertical shifts. That's when our horizontal asymptote would actually shift with our graph, which is kind of interesting. All right, let's go. We got one more example for this one. And then that is it for 4.1. Okay, so applications. All right, so we're looking at compound interest. Okay, so we have this lovely large function here. A of t equals p times 1 plus r over n, all raised to the n plus t power. Okay, so what does a of t mean? A of t is the amount after t years. P is the principal, or the amount invested. T is the number of years you have invested that amount. R is the interest rate that you've invested at per year. And n is the number of times your interest is compounded. All right, so here's the different values for compounding. So if it's annually compounded, annually means once a year, so n would be 1. Semi-annually would be twice a year, so your n would be 2. Quarterly would be if the year was split into 4, so that's going to be 4. Monthly, well, how many months do we have in a year? 12. And daily, how many days do we have in a year? A lot of days, 365. Or whatnot. If they're going to do daily, I would check to see in the instructions at what value they want you to do daily. Okay, weekly.